of V. Clear enough? Then here's the rules. If you can show, number one, that W is not equal to the empty set, right? If number two, you can show that X and Y being in W implies that X plus Y is in W, right? And three, if you can show that if C is a real number and X is in W, implies that C times X is an element of W, then W is a subspace of V. This is the subspace theorem, sometimes called the subspace test theorem, sometimes called the two-step subspace test theorem, sometimes called the three-step subspace test theorem. Sometimes people make this a step and call it a four-step subspace theorem. I don't know. Various things have been tried to impart the idea of it to students. It's really not that complicated, though. Let me put it into words a little bit more. This is closure of addition. For W, right? This is closure of the scalar multiplication. You need both of those. But the proof of this theorem, which I won't go through except to just kind of sketch it, is basically once you have this closure of addition and closure of scalar multiplication, if you sort through the axioms, like the fact that this is a subset of V, and it's already true for vectors in V, well, vectors in W are also vectors in V, so they satisfy those axioms. So like the axioms just immediately transfer over to W. The only thing you really have to worry about is the closure of addition and scalar multiplication. But those we assume can be shown to be true. So we have that data. So we get the W's of vector space. But this is such wonderful news because that means all I have to check are these couple things as opposed to 8 to 10 axioms, right? This is much, much nicer. So let's actually look at an example and see how that works. This is about the proofiest this course gets. But it is necessary to have this discussion. Otherwise, we won't be able to make sense of some of the nicer toys we have to play with in here. Okay? So I try to remove as much as I can of the proof element in this course, but this is one of those places where we need to do a little bit. So here's an example. Consider you got what?
Oh no, I'm out of paper.
Oh. So let's consider symmetric matrices. Right? So V equal to Rn by n, this is our sort of ambient vector space. That's the universe in which this example lives. Let's give it a name. Let's say W, because I've got W on the brain today. Let's see here. W equals to A such that A in R n by n, so it's an n by n matrix, such that what? Here's the condition it meets. A transpose equals to A. So we'd like to show that that is a subspace. Now let me tell you something more about this subspace test theorem. I said show it's non-empty, but you might as well replace this with show zeros in there. Show zeros in W. That implies that W is not empty, right? If the zero's in there, you're good to go. So 0 is usually a nice thing to show that it's actually in there, so the set's not empty. It's pretty easy to find 0. So here, notice that 0 matrix transposed is what? What's the transpose of the 0 matrix?
The 0 matrix.
Indeed. So what does that say? Zero is an element of W, right? 0 is a symmetric matrix. all right, in words. Not that you need to write those words, because those words are, I mean, it's already clear from what I've wrote there. This means element of. You guys know what this bar means? This is such that, right? You guys know set builder notation? I guess I've been using it for solution sets, so if you had trouble, you should have talked to me about it already. Yeah. Now what's next? We're on to number 2. So we finished number 1. Number 2, let's let A and B be in W. Then consider A plus B transpose. A plus B transpose is what? We know properties of transposition, right? The transpose of the sum is the what? Sum of the transposes, right? So then what? What did we assume about A and B? Right? A transpose is equal to A. And B transpose is equal to B. Why? Because we assume that they're in W, right? So this is A plus B. So what have we shown? Thus, A plus B is an element of W. 3. If C is a real number and A is in W, then note that C times A transpose is C times A transpose is C times A. Therefore, C times A is also in W. Being a little bit less verbose on my reasoning, if you don't mind. But again, it's because we're assuming A is in W, right? We get that data to work with. We're not working with an arbitrary matrix. We're working with the symmetric matrices, trying to prove a property about them. Namely, that they're closed under addition, scalar multiplication. In fact, they are. Bam! By subspace test theorem. Hence, W is a subspace of R n by n. Let me tell you where we're going. Yeah.
So, like a test or a quiz or something, it would be like prove that this is a subspace, and then we run these tests.
Mm-hmm.
Okay.
Right. Yeah. I'll try to do a few more of these, but let me just give you the big picture where we're going because we're about out of time. So, just to ruin the story for you, the ultimate story is just this: any vector space is really just Rn in disguise. Well, that's not entirely true. The finite dimensional vector spaces are just Rn in disguise. Some of the vector spaces I have had up here are infinite dimensional. They go on and on. Polynomials. What's the highest order polynomial? X to the n. I say it's x to the n plus 1 then. Haha, I beat you. See, I can always add another power, is the thing. The polynomials go on and on, right? That n is not fixed. So there's polynomials of arbitrarily high order. That's why the vector space of polynomials is infinite dimensional. It goes on and on. In contrast, like 3 or 4 dimensional vectors or 2 by 2 matrices, right? 2 by 2 matrices, unqualified 2 by 2 matrices, are essentially just a copy of R4 written in a weird way. All right? And so what we're ultimately going to describe in here pretty soon too, because I'll condense it down for you guys, is that a vector space has something called a dimension. The dimension is the number of vectors you need to build every other vector in a unique way from those basic vectors called the basis. And so the number of vectors in the basis is called the dimension. We have something called a coordinate map that goes from this abstract vector space to Rn. I'll build that for you guys. But the long story short, the takeaway from all of this is that ultimately we're going to see all of the finite dimensional vector spaces are really just Rn in disguise. So So a lot of the things we've already done with column vectors, we can steal and still do for these abstract examples, but we need a little bit of creativity for that. The more interesting thing, of course, is just the idea of putting coordinates on things. It gives us a more general sense of what a coordinate system is, and that is useful in its own right. We'll be able to do things like, I'll show you guys how to build, for example, like the parameterization of a torus. Say if we have a circle, say in the like YZ plane, we can look at something called a rotation matrix, and I can use that rotation matrix to rotate the circle around the axis, and by doing that, we'll make a torus. And I think I can show you how to do that, how to like create those sorts of things and so forth. But I don't know. I'm not sure where that fits into this right now, but I think it's something I'd like to show you guys. So I'll try to get back to that. But anyway, we're loosely in chapter 3. This is, of course, not on the test. I said that nothing. I wouldn't agree that nothing here would be not on the test. That's not honest. There are things we did today that very much could be on the test. Like this right here could be on the test, right? We talked about symmetric matrices. I might ask you like a true-false question. Is the is this a rule for a matrix transposition, right? This is something that might be on test 1. Now, prove that that's a subspace is not on test 1, right? But the calculations you actually need to do to show that, some aspect of those could be on test 1. But I think test 1 is mostly, though, about row reduction, right? And the structure of solution sets, that stuff. That's our lion's share. And a token application problem or two, which I know I owe you guys the mission. I have several problems written. I'm just not quite done with it. I'll make sure I don't rush through it, because when I rush creation of homework sets, bad things happen. Bad things. So just give me a second to put it together so it'll be nice for you and hopefully not too long, because I'm planning to solve it too, and I don't have much time. Yeah.
I know you hasn't taught this class in a while, but
Uh-huh.
are there tests? Are there previous tests?
Are there previous tests? I mean, you could.
So that we can like expect what are the formats of the questions, I guess. Or is this going to be like the mission?
I think it's going to be like the quiz. You could look at the quizzes. You could look at the mission. You can look at my old linear algebra tests if you kind of set aside the proof questions. It's probably still relevant. I mean, like I don't see myself asking you to prove that the product of like the sock-shoes theorem for transpose, right? Like the fact that A times B transposed is B transpose times A transpose. Like it's very unlikely I ask you that in the test. And the flip side of things, I have asked that on the first test of linear algebra 321 for about 3 semesters now. I don't know if students have noticed this or not, but I don't know, like the answers on that question aren't getting appreciably better every semester, so I assume that no one's picked up on this yet. Like, but on the flip side of things, right, you'd think that no one would get the definition of a function wrong in Sperano's first test in calculus either, right? Because Sperano always asks what's the definition of a function in the first test in calculus. Like, I think it should be. Maybe this knowledge does not get passed down from upperclassmen to freshmen. Is that the thing? No. Someone should start a Facebook page. Dr. Sperano's first test.
We did that in computer science. It's called the emergency Shannon cow. And it works its way down to that class.
That's funny. I mean, we don't have fraternities, right? If there's a fraternity, they'll have there's some sort of file cabinet, and they have all of the tests ever given by every professor at the university. I mean, that's like the main function of a fraternity, I think, right? And drinking. I mean, I don't know. I was never in a fraternity, but I heard about these things because fraternities are a thing at NC State, right? They exist. They.
That would probably be the only practical function of a fraternity, but I'm not exactly sure it's the main one.
Ah. Yes. Do you have fraternities?
No.
Okay, I just checking. I see some painting out there sometimes that makes me wonder, but yeah, the rock painting, it's somewhat frat-like parts of it. No?
Just honor society.